Hey everybody, and welcome back to Linear Algebra Online. So the plan for today is to talk about determinants actually, but I want to start off and talk about just another kind of conceptual eigenvector problem. And we really need to talk about determinants because when we compute eigenvalues and eigenvectors, we start off with this determinant problem. And so we need to learn some kind of tricks to compute determinants basically easier. But to start off, so this matrix right here is the matrix that projects a vector onto a line with direction vector 4/5, comma 3/5. And if we think about that, right, actually let's just kind of draw it really quick. So we got, let's say that's 4/5, and then that's 3/5, right? So we're talking about projecting things onto that line, right? And if you think about that, right, then the eigenvectors should either be, the eigenvectors are the vectors that just stay like in their span, right? So we basically would have, certainly anything on the red line would be an eigenvector because it would just, stay on the line there that we're projecting onto. And then the other options are basically the vectors that are like perpendicular to the red line, right? And those ones would stay on their span, right? They're going to stay on this line, and they're just going to get smushed down to the red line there somewhere. So those are the eigenvectors. They're going to be things like that. And the values, right, for the yellow one, we basically should have like lambda equals 1, right? Because there's basically should be no scaling at all. Like the projection onto this line would just keep these vectors the same because they're already on the line, so there's like no scaling going on. The other ones, though, definitely get scaled. They get scaled by 0, right? Because if you smush this vector down to the red line, you'll have no more of it, right? It's like literally gone. So its scale factor is actually 0. It's gone. So those are my values that I should get. And then the vectors should basically be a scalar of the red vector or something that's perpendicular, right? So we know, to get a perpendicular line, just like in algebra, right? That green vector should basically be a flip and negation of this one right here. So, something like negative 3/5, comma 4/5. So that, this should be an eigenvector, and anything parallel to that is also an eigenvector. So that's basically the conceptual idea, and those are going to be what we'll see. But just to kind of show you, I'm going to kind of sketch out the actual calculation of it. So we start off with determinant of a minus lambda I, and we're going to set that thing equal 0, right? So 0 equals the determinant of 16 over 25 minus lambda, and then 12 over 25, and then 12 over 25 again, and then 9 over 25 minus lambda, all right? And if we go and compute that determinant out, we're going to get this. And then that's a 9 right there. And then if you go and multiply this out some more, you'll get this. And then, you could just solve that quadratic with like, pretty quickly, because you can just go and, these two things are going to cancel. You'll get lambda squared minus lambda, which you can take out a lambda for. And then you have lambda minus 1 equals 0. And so, here is your 0 that you're getting, and then here is your 1. Okay, so those are my eigenvalues, right, which we expected to get. And then, the way we do these things to get the vector, we basically just augment the we just augment the vector, like the matrix A minus lambda I with 0, plugging in each lambda, and then reduce from there, reduce the matrix, and see what we get. So we'll just do the 0 first. So when you do a minus 0I augmented with 0, it's really just, a augmented with 0. And if you do that one out, you should get the following matrix. And so from this, you can see that x1 just needs to equal negative 3/4 x2. And so the eigenvector for 0 is basically anything in the span of negative 3/4 comma 1. And that one, if you multiply it by 4/5, right, you would get this green one that we kind of predicted here. So we're getting that one, right? And then you do the same kind of thing for lambda equals 1. So you got a minus, 1I augmented with 0. And if you do that one out, you'll get this matrix. And that's the one where then you can see that x1 equals 4/3 x2. And so the eigenvector, for 1 is anything in the span of 4/3 1. And that's the one where if you multiply by 3/5, right, you would get the things parallel to the line we projected onto. But this is just kind of a good review problem to kind of make sure that we understand what's basically going on with eigenvectors and eigenvalues. All right, so the main goal for today is to talk about determinants. And we kind of mentioned some of this before when I talked about the inverse of a matrix, but it's good to kind of review this too. So whenever you do a determinant, you actually are doing these, you're working with these cofactors. And, really the first time you ever see this in math is when you do a cross product. You're doing a determinant, which is why this is all connected here. But, there is a pattern with even the cross product, this plus minus plus pattern. And that you can see here, and it would really continue. If you were doing a 4x4 determinant, you just keep that pattern going and going and going. And this is just the definition of an inverse again. It's the transpose of the matrix of cofactors, which is this thing, the adjoint matrix of A, and then it's divided by the determinant of A. But basically, the idea is if you were doing this one right here, in blue, you would just blank out the column and the row associated with whatever entry you're at, and then whatever is left over, which in this case is this, 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 and this, right? You do another determinant, basically. So when you do a 3x3 determinant, you reduce down to a bunch of 2x2 determinants. If you do a 4x4 determinant, you're going to expand along these entries and do 3x3s first. Then from those, right, you have to do 2x2s. So you get a ton of nested determinants, and it's computationally a pretty slow thing to do, to be honest. And so really the goal for today is to talk about tricks to make it faster so we don't have to do it the slow way every single time. So that's the plan. All right, so the first thing I want to do is basically just, we can just use a calculator just to kind of do it faster here. But I would want you to see sort of a connection between the determinant of A and A transpose. And then by hand, see what you would get if you did the cofactor expansion that we were talking about in the last slide along this third column, okay? So if you do that, you'll notice something really nice happening. And you can see that this third column is a really easy column to work with, okay? So if you do it on your calculator, if you do, plug this all in, and then you get its transpose, and then you take the determinant of both those. What you would notice is the determinant of A is equal to the determinant of A transpose, which is really nice. And if you do it out by hand along that third column, okay, this one, I think I can even still fit right here. When you do the first entry, right, you get the 0, so then you're going to do 0 times a 3 by 3 determinant, which I'm not even going to bother writing because it's 0 times it, right? And then, so that term's positive, so then the next one's negative, so negative 2 times a determinant. This one I actually do need to worry about. So if I blank these out, right, I have, so I have stuff in here. I have minus 2 times the determinant of 2, negative 3, 1, 1, negative 1, 3, negative 2, 1, 0. And then I would have plus 0 times something, right? And then minus 0 times the determinant of something else. So basically now the problem has boiled down to just negative 2 times the determinant of 2, negative 3, 1, 1, negative 1, 3, negative 2, 1, 0. And if you do that one out, okay, you're actually going to get that you're going to see that it's the same thing as determinant of A, and also the same thing as determinant of A transpose. And what this very long-winded thing here says is something really nice that I'm not going to take time to prove. It's really not too bad, but you can just kind of use this fact. We're just trying to speed things up. So what it's basically saying is what I wrote over here. It says that you can calculate a determinant by expanding along any row or any column. It doesn't matter which one you pick. And so I'm going to erase this. When I see a matrix like this, instead of blindly just like, when you do cross products, you're kind of used to just expanding along the top row. But that is definitely not the best way to do all these. This one, the best way would just do the third column. And it's nice that the determinant of A and A transpose are the same kind of thing. That just kind of gives us some sort of, I think, confidence that we can actually expand along columns and also rows, right? Because that's really all we're interchanging here. So that's kind of one of the other motivators, I think, for why you can really do it along any row or any column. So when you do determinants, don't just blindly do like this column or something. Just don't get used to just thinking you're going to always do the first column or the first row or something. You really want to look for whatever one is easiest. All right. And there's another really kind of nice, easy determinant structure that I want you to see here. And this one, I want you to kind of see it by hand, okay? So this matrix right here is, just a triangular matrix. And, if I was using what I just talked about in the last slide, I would want to expand along the first column, right? Or I guess the bottom row. Both of those would be the two best contenders. I'm just going to do the first column. So if I start doing this, right, I'd have 2, and then times the determinant of negative 3, 1. Actually, for time reasons, I'm going to plug in the rest here really quick. All right, so that would be what I get, when I blank out this row and column. I have that matrix in there to do the determinant of now. So then, the rest of them are going to be 0, right? Because you're going to do 0 times, you'd blank out this and this, and you'd have 0 times something, so that's gone. Then you'll have 0 times something, 0 times, so all those other entries just provide no information, right? So then you would take this and it all kind of starts over. Now you're doing, 2 times the determinant of this big chunk. And for the determinant of this chunk, I would look at this column. And I would expand along that. So now I'm going to do 2 times 3 times the determinant, right? Blank out, 160,052, 0, -1. And you might see where this is going. The other entries here are going to provide nothing. So those just, are not important. So then you just keep going. You got 2 times 3 times this determinant. So we can, actually, let's just do a different color. So now I would expand along, like, say, 1, 0, 0. And I would do 2 times 3 times 1, determinant of 5, 2, 0, -1. And then, again, let's just expand along that. So we get 2 times 3 times 1 times 5 times basically -1, right? It's really like a 1 by 1 determinant, but that's just one number. And so you can kind of see that what I really want you to take away here is that if you have the determinant of a triangular matrix, it really just equals the product of the diagonal, okay? It really just, if you see it out once like this by hand, I think it's very easy to believe that. It's really just a nice byproduct of having all these zeros down here. So anytime you see this sort of triangular structure in a matrix, just know that you can actually just expand along, you can just multiply along the diagonal, and that actually is your determinant. That really would be it. Should probably make that a little more clear. That's a multiplication, not a negative there. So that's one big shortcut, basically, that we can use. That one's going to be very helpful. All right, so this is actually something straight out of the textbook, and it's just kind of a neat thing that I wanted to make sure that you guys kind of saw. So computing these determinants is a crazy long computation, and it actually involves, so in computer science, there's actually this stuff, there's things where we classify as computationally like hard or easy. Those are actually like terms. And determinants are actually really hard. They require a lot of calculations. There's actually more than n factorial calculations for an n by n matrix. And this is kind of a neat example of showing you how crazy hard they are. So if you had a 50 by 50 determinant, which honestly in the scheme of things, 50 by 50 is not that big. There's a lot of matrices that I worked with that were like 10,000 by 1,000 or things like that. And, you could easily run into like 1,000 by 1,000 or some sort of square matrix like that. 50 by 50 is honestly fairly small in the scheme of things. So this is not even that big, okay? But even for that one, so it requires more than 50 factorial operations, and 50 factorial is this 3 times 10 to the 64th. And for a really fast computer, even this is crazy hard, because it's saying that if you could perform 10 to the 12th operations per second, okay, that's a trillion, it would take approximately 3 times 10 to the 52 seconds, or almost 10 to the 45th years to finish those calculations, all right? And the age of the universe is 10 to the 10 years. So even for a very fast computer, a 50 by 50 determinant would take more than 10 to the 30th times the age of the universe. So hopefully that sells you on why there needs to be something else. And honestly, I don't think your calculators can do a 50 by 50 determinant, but for sure if you opened up like something like Mathematica, Python, these kind of things, they compute those no problem. And the reason they do it is basically they have tricks that are built in, and they're using those tricks to speed things up. And actually there's a few other tricks that like computer languages have. There's some things where there's something called parsing. So we don't really need to get into computer science, but A parse is like a thing where we kind of ignore some entries that sort of don't matter, and it helps simplify some of the numbers in there. So sometimes we do stuff like that, but that's like a computer science thing. If you go study CS, you'll learn about some of that. But these are just, I'm not going to go and prove them, and I think actually the proofs of some of these are in the text, and they are some good examples and kind of good proofs probably to go look at. But one of the things, these are all used, I guess, to help speed up computations with determinants. This one is really nice. It's saying that if you have a determinant of a product, then it's equal to the determinant of A times the determinant of B, which is much easier, right? So like if you have a product that gave us a really large matrix, then, you could just split it, it's saying. And there's actually ways to factor matrix products like this. So we actually sometimes can unpack a product and figure out these two determinant easier because they might be simpler once they're factored out. This is something we already talked about. Very nice property, and sometimes one of these might seem easier, but really you could just expand along any row or column, so it doesn't really matter. Determinant of A inverse is 1 over the determinant of A, which is nice. This is another one that can definitely speed a lot of stuff up. Basically, K is just a number here, and it's saying that if you have K times a matrix A, then K to the n, whatever the size is, times the determinant of A would be equal to the determinant of Ka. That one you can probably see pretty quick if you just make like a 3x3 determinant, a 3x3 matrix, and you can kind of see where that pops up, I think, pretty quick. And then this one is a little more confusing, but it's saying that if A is an n by n matrix and B is just obtained by interchanging or switching any two rows or columns of A, then the determinant of A and B are just different by a negative sign. And that one is also not so bad to see, and it's related to the sign part of the determinant, so the plus and minuses. And you could kind of figure that one out too if you just switch two rows. You kind of would be able to see why that pops up. But all of these and some more tricks too that are kind of computer sciencey tricks are used to help speed up computations. I really don't mind once our matrices start to get kind of big if we just use our calculators to do these determinants, but I do think it's good to see stuff like this because you can see how hard it is to sometimes compute a determinant.